Okay, picking up. So here is the official statement of the first derivative test, and it talks about changes, positive and negative, negative to positive, of the derivative. But for me, hard to close my eyes and visualize, unless I'm really sophisticated, and some of you might be way more sophisticated than I am, but it's hard for me to close my eyes and visualize a positive derivative changing to a negative derivative and what that meant for the critical number. I can't close my eyes and see it. So I like to modify this just a little bit to something that I can close my eyes and envision. And what I'm going to do is put together some things that I know. That one of the things I know we just learned, that if the derivative is positive on an interval, the function is increasing. If the derivative is negative on an interval, the function is decreasing. And if the derivative is 0, the function is constant. So putting those two things together. So if I look at the first one that says if f prime changes from positive to negative. Well, if f prime is positive, the original function was increasing. And if f prime is negative, the original function was decreasing. And so instead of saying derivative positive to negative, I could say function increasing to decreasing. Positive derivative was increasing, negative derivative was decreasing. So I could say this: if f of x changes from increasing to decreasing at x equals c, there's a local maximum there, because I can see that. So over here, f prime positive, or f of x increasing, I'll do that over here. On this side, how about yellow? Over this side, f prime of x negative, f of x decreasing. And the only way that could happen if you pass through a critical number is that you pass through a local maximum. And so I tend to say, instead of necessarily thinking derivative positive, derivative negative, I tend to think function increasing, function decreasing had to go through a local maximum. Same thing on this one. So on this side, we have the derivative being negative or the function decreasing. Over here, we have the function, the derivative being positive, or f of x increasing. Well, if I pass through a critical number, I had to find a local max. That I can close my eyes and see. I can see, oh, my function is falling, then my function is rising. I had to hit a low point. I had to hit a local maximum. Same thing over here. I can close my eyes and I can envision my function increasing, my function rising, then my function falls, my function is decreasing. Well, the only way that could happen if I passed through a critical point was for me to hit a local maximum. And if fx doesn't change signs, you found nothing. So we're going to take all this information and we're going to start sketching things. And we're going to try to make good graphs. Nicely labeled good graphs are our goal. So, how to find intervals on which a function is increasing or decreasing, or how to find local extremes. You read either one of those two instructions. Find where it's increasing, decreasing, find the extreme values. That's going to trigger these steps. Anything that says increasing, decreasing, extreme values, here are my steps. 1, find the derivative, not surprising. 2, find the critical numbers. Have to find the critical numbers because local extremes occur at critical numbers, but not all critical numbers are local extremes. 3, using the critical numbers, make a sign chart for the derivative. A, subdivide the real number line into intervals using the critical numbers from smallest to largest. B, pick a test value in each interval. C, substitute each test value into the derivative and determine the sign of the derivative. And we'll go through that slowly. 4, label each interval of increasing or decreasing. Recall if f prime of x is positive on an interval, f of x is increasing on that interval. If f prime of x is negative on the interval, then f of x is decreasing on that interval. 5, identify the local extreme values and their locations using the first derivative test. Okay, so starting to practice here. Answer the following questions about the function whose derivative is given below. So we aren't going to have to do step 1. They gave us the derivative. So A, critical numbers. There are 2 types of critical numbers where the derivative equals 0. So I'm going to set that dude equal to 0 and solve it. Clear that fraction. Equations with fractions. Clear the fraction. So it cancels over here. And so I get e to the x times x minus 4 quantity squared times the natural log of x minus 3 equals 0. And then we've talked about this before. This is factored equal to 0, so we can split it up. So I can have e to the x equals 0, x minus 4. I think I'm going to go on to the next page so I have more room. So I'm going to have e to the x equals 0, x minus 4 quantity squared equals 0, natural log of x minus 3 equals 0. Then I solve each one of those. Exponential equation. Take the logarithm of both sides. Because natural logs and natural exponentials, those are inverse functions, and when I do them both, I just get x. But this is undefined. If you forget, ask your calculator. Make sure your calculator, it wouldn't matter in this case, but in general, make sure your calculator is set for real numbers. Natural log of 0 is undefined, so there's no solution here. It's not that we did anything wrong, just that it didn't come up with a solution. Here, without much fuss, and I'm not going to go through that, that's going to be x equal 4. And over here, this is going to be the natural log of x equals 3. So, similar idea. Here, this was an exponential. The opposite of exponentials were logarithms. Natural exponential, the opposite of a natural exponential is the natural log, the inverse function. Here, we have a natural log. Exponentiate. Raise both sides to e. Or let's put it this way, use both sides. Put it this way. How do I want to put this? We'll just put exponentiate both sides. Using e. So this becomes e to the natural log of x equals e cubed. The natural log and x, those are opposite operations, inverse operations, so we get x equal e cubed. So my critical numbers start out as, well, I'm going to do one more thing, then we'll say what the critical numbers are. Now, there are 2 types of critical numbers. Recall, there are 2 types of critical numbers. Still need where f prime of x equals 0. So recall we had this. We had f prime of x equals e to the x minus 4 quantity squared, natural log of x minus 5 over x minus 5. So f prime of x, oops, I wrote that wrong up here. Not that we still need f prime of x equals 0, we have that already. We still need where f prime of x does not exist. There are two types of critical numbers, where the derivative equals 0, we found those, 4 and x e cubed, and then where the derivative doesn't exist. And so in this case, f prime doesn't exist where that denominator is 0, and so I'd get 5. And so then you would happily type this into the computer, that my critical numbers were 4, e cubed, and 5, and it would say, no, it's not, you're wrong. It wouldn't say that, you know, you get my idea. It'd just tell you we're wrong. And I purposely left off something here. Here was the original problem for x not equal to 5. And so right there in the original problem, they're telling you that 5 is not in the domain of this function. 5 is not to be used in this problem. That's misleading. 5 is still a very, very, very important number. It's just that I can't label it a critical number. Critical numbers must be in the domain of the function. They've told us 5 is not in the domain. So it is not legal for me to label it a critical number. But it is still a vital number for the work we're about to do. That it's going to ask me where things are increasing and decreasing, and that 5 can make a world of difference about increasing and decreasing. So for me, always, always, always calculate where that denominator of that derivative is 0. Sometimes it will be called a critical number. Sometimes it won't. I don't care that much about the language there. Where the derivative goes to 0, or excuse me, not where the derivative goes to 0, but where the derivative is undefined, where the denominator of the derivative goes to 0, is a hugely important number. There will be times when we shouldn't label a critical number for technical reasons. But it's still a very, very, very important number, so I'd rather have you always calculate it and accidentally mislabel it as a critical number than not calculate it at all. In this case, it's not technically a critical number. So that right there, so not technically a critical number, but still a vital number. And so we do absolutely need it for the work we're about to do. So in this particular case, my critical numbers just turned out to be x equal 4 e cubed. But again, emphasis. For me, if you call that a critical number, I will be fine. Technically, it's not. The computer won't like it. But it's still a number we need for all our future calculations. So always, 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 if the derivative is a fraction, set that denominator equal to 0 to find where the derivative doesn't exist. So there are my critical numbers. We'll go on to the second part of this problem in the next video.